Okay, thank you very much to the organizer for the invitation, in particular to Andrea for inviting me to give a talk and present some of the main idea of birational geometry, and in particular the minimal model program. So I was told to give a gentle overview. So many of the topics I will talk about will be introduced in a very simple way, although sometimes I will use some technical language. Okay, so the objective for today is to say something about birational geometry, and at the end to describe some of the possible direction in the future for birational geometry, at least those that I'm particularly interested about. But let's start from the very beginning. Let's consider the goal of the main object of study of birational geometry. So like most of you or all of you know, a projective variety is defined as the zeros locus of some homogeneous polynomials. In this case, for this lecture, we will focus only over the complex numbers. So we'll assume that these polynomials are defined over the complex numbers. Nevertheless, the theory becomes interesting also if we allow different fields. We can choose them to be algebraic closed fields, but also non-algebraic closed fields, or even rings. There are a lot of new developments of algebraic geometry over the rings, and particular birational geometry over the last few years, which are very, very interesting. But to keep things simple, let's focus over the complex numbers. So our projective variety is defined as a geometrical shape given by the zero locus of these polynomials over inside the projective space of dimension n. So first of all, what is the dimension of X? Well, I don't want to give a very precise definition, but locally, we can think of X, at least in the smooth locus, in the place where it's regular, without really defining what regular means. It looks very much like an open subset of Cn, at least locally analytically. And we call n to be the dimension of X. Of course, bad things can happen. It could be that there are different components of different dimension. But for today's lecture, let's suppose that X is given by a single component, which is almost everywhere regular. So a very first remark about this number will appear everywhere in these lectures. The dimension is that if we think of our variety defined by homogeneous polynomial, then the dimension, it's always at least the dimension of the projective space where we're considering our variety, minus the number of polynomials which define the variety. Of course, this is not a sharp inequality because we could use, for instance, all the polynomials to be the same. We're not going to get anything more interesting than by just considering one polynomial. And there are more difficult cases, so it's just an inequality. But at least we're sure that if we work with the complex numbers, if we don't have too many polynomials, then this is a non-empty set. So what is the goal of birational geometry? Well, somehow is to give an answer to this very vague question. Can we classify projective varieties? Of course, the word classify in mathematics might mean different things for different people. Even if we only ask to people in algebraic geometry or even people in birational geometry, it's not clear what exactly classify means. And it's not even clear whether it's possible to do so, but at least we can start. We can try to find boxes on which projective varieties belong, or we can find some structure which represent varieties. So in other words, some structure for each point represent a variety. We'll see this in a bit. But let's start from a very simple example, an example that has been known for a long time, which is the set of varieties of dimension 1. So these are called algebraic curves by algebraic geometers because they have dimension equal to 1 over the complex numbers. But in analysis, they are referred to as Riemannian surfaces. In this particular case, as compact Riemannian surfaces. And the reason why they're called surfaces is because they have a real dimension equal to 2. So for a long time, this object has been studied, and we have somehow a good understanding from many points of view of these objects. And I think everyone will agree, whether they are algebraic geometers, differential geometers, and so on, that it makes sense to divide this object into 3 families. So this is the beginning of a classification. The first family is given by, just this Italian word there, sorry, by a sphere, a P1. Okay, it's only one element. The second family is given by elliptic curves or torus, which are given by, I mean, they look like a donut, but it's a algebraic curve or a Riemann surface of genus 1. And then we have hyperbolic curves, which are donuts with more than 1 holes, which are many. I mean, of course, first depends on the genus, which can be as large as we want. But we'll see that even if we fix the genus, there are many of these curves. Okay, and each of us might have a good idea why we want to define such a classification, why we want to define curves, algebraic curves, or Riemann surfaces this way. From a differential point of view, I mean, if we care about the differential geometry of this object, we know that the sphere emits a metric with positive curvature. Elliptic curves emit a metric with 0 curvature. We can even take, sorry, in the case of sphere, we can take, of course, the curvature to be constantly, to be constant, not only positive, but positive constant. And in the case of hyperbolic curves, we can also find a metric with curvature negative, which is constant, so negative constant. And of course, many of the geometric properties depend on this fact. From a geometric point of view, from a topological point of view, we already mentioned about the genus. This is a very simple fact. The sphere has genus 0, the elliptic curves have genus 1, and the hyperbolic curves have genus greater than 1. Of course, this alone is not very interesting, but there are many topological properties that are depending on this classification. So for instance, the easiest one is the fundamental group, P1. Pi1 is equal to 0, is trivial in the case of the sphere. It's huge in the case of hyperbolic curves. What does it mean? It's a really big group. It's highly non-commutative. And of course, it becomes bigger and bigger when the genus becomes bigger and bigger. And it's somehow in the middle in the case of elliptic curves or the tori. It's given by z plus z. And again, something similar happens for many different points of view. Like, for instance, let's see one more. We can ask ourselves, what is a set of rational points? So what does this mean? Naively speaking, although this is not quite true, we know that these are object-defined zeros of polynomials in ZPN over the complex number. So we can ask how many points have rational coefficients. This is not quite true. We might have to extend it by a number field, not only by taking rational points. But besides this technical point, it's well known that the sphere has a huge set of rational points, and many rational points, again allowing to extend the field, the ring or the field of rational points a little bit. In the case of hyperbolic curves, on the other hand, it's completely opposite. By a famous theorem of faulting, a very deep theorem of faultings, this set, no matter what we take as a number field, it's always finite. And in the case of elliptic curves, again, it's somewhere in the middle. Is not finite, is not huge, it's finitely generated. This is a theorem by Mordell. And again, there are many other properties that depends on this classification. For example, we might be interested in the group of automorphism of these algebraic curves, and this is somehow related with the dynamics of the variety. So in the case of the sphere, the automorphism group is very large, it's very big. In the case of hyperbolic curves, it's always finite, very often it's trivial. And in the case of elliptic curves, again, it's something in the middle. So it depends who you are. If you're an arithmetic geometer, a differential geometer, or an algebraic geometer, you might have different reasons to classify this object. but the classification will be the same, or at least dividing them to three different boxes would be exactly the same. But we can do even better than this. So for a long time, it's been known that there exists a quasi-projective variety, which is denoted by MG. So quasi-projective variety means that it's an open subset of a Zariski open subset of a projective variety. So in other words, if we compactify this object, will be a projective variety. So for any positive integer G, there exists a quasi-projective variety such that each point of this variety represents a isomorphic class of a curve of genus G. So this variety has been extensively studied. So first of all, it has dimension 3G minus 3. And this somehow corresponds to the fact that the bigger the genus is, the bigger this object is, the more curves of such a genus there are. So first of all, the geometry of this object is very interesting. There are many results that appeared over the last decades about the structure of this as a variety. But also from a geometry point of view, algebraic geometry point of view, this is somehow answering the question of whether we can classify curves. Of course, this is not a completely satisfying answer, but it's quite a good answer, meaning that we have an object such that for each point of this object, represent a isomorphic class of algebraic curves. So there's a one-to-one correspondence up to isomorphism between curves at points of this variety, of this quasi-projective variety, which is somehow the best we can hope for a classification. Of course, it will not give us understanding of all the curves, but somehow it gives us a way to describe all the possible curves of a fixed genus G at the same time. So somehow when we think of classification, we think of constructing moduli spaces. So object that looks like this. And for varieties of higher dimension, this is also very interesting, a very extensively studied object in algebraic geometry. So, but instead of working on moduli space, let's go back to this attempt to classify our varieties and divide them into boxes. So the boxes here will be much bigger, we'll see, and it will be more like a forest. But the idea somehow is similar. But before doing that, we're not anymore constrained between only fixed one isomorphic class. And the reason why this is true is because it's very easy to produce many surfaces or many varieties in higher dimension that looks like a given one. So we fix one, it's possible to change in such a way that there are many, many more. So in algebraic geometry, it's not quite like differential geometry where we can deform things by cut and paste or by changing the shape. In algebraic geometry, operations are different. And this is somehow the goal of study of Birational geometry. So let's consider this example. We are considering now the case of algebraic surfaces. So in a particular dimension, complex dimension equal to 2. Let's suppose that this first surface is smooth, and let's fix a point on the surface. So what we can do is to construct the blow up of such a surface. So what is this? So without giving too many details of how to construct such a blow up, the idea is to look at all the infinitesimal, all the lines that pass through the point, around the point we're fixing. But without giving too many details, it's possible to construct a new surface, which in this picture, it's denoted by BL, as for blow up, of the variety X at the point X, or we can call it Y, and which also emits a morphism B from Y to X in such a way that if you remove the point below from X, and if you remove E, which is the preimage of the point on Y, then these two objects become isomorphic. So outside the point, we didn't do anything. what happens is that we replace the point X by a curve E, which happens to be always isomorphic to P1. So it's a sphere. So in other words, we take a surface, we remove a point, we add a sphere, and we obtain a new surface. And we can do this game as many times as we want. So as I mentioned, Y is called the blow up of X at X. And the reason why we study this is because we obtain this way many new surfaces. So this is still a smooth surface, so we can repeat the process. And somehow we need to understand how these surfaces sit together. And this is the role of Birational geometry. So before we continue, let me give a remark. The surface Y compared to the surface X contains an extra curve. The extra curve is P1. And this curve has positive curvature, as we saw before. So in a way, to compare Y and X, and this is very vague, Y contains one extra curve compared to X of positive curvature. Of course, this is not very precise, but it's just to give an idea how Y and X are related. So in a more technical language, if we take KY to be the canonical divisor of Y, and E to be the exceptional locus, in other words, the preimage of the point that we're blowing up on X, then KY times E has negative intersection. So minus KY times E is positive. So KY can be thought of the first chain class of Y, if you know what it means. If you don't know what it means, it's not going to affect what we're going to say later on. Okay, so this is just to make a little bit more precise what we were saying before about getting rid of a curve. If we go down from Y to X, we get rid of a curve of positive curvature. So the curve will satisfy the property that minus KY times E is positive. Okay, so now we see why we can find a forest of surfaces. The reason is because if we start from any smooth surface, any given smooth surface, then we can find many more by applying this single process that we explained just now. So for instance, let's take 2 points instead. What I could do is to blow up both of them, and I get a new surface, which maps over the blow up of each of the points we consider. Or alternatively, what we can do is to blow up one point, in this case x1, as in the picture, and then take a point y1 on the exceptional curve e1, on the new p1 that creates it, and blow up the curve, and blow up the point, sorry. Okay, by doing this way, it's clear that we get as many surfaces as the number of points, repeated as many times as we want. So we really get lots of surfaces, infinitely many surfaces, but not only infinite, I mean, a big set of surfaces by just repeating this game as many times as we want. So now the point of Birational geometry is that it's no point to consider these surfaces as very different from each other, because otherwise there are too many objects to study. So the idea is that, can we consider all these surfaces in one single box? And can we consider this box individually as a single object? So in other words, we want to create some kind of equivalence in such a way that all these surfaces are the same in this equivalence. And then we study the equivalence class of surfaces after we take this equivalence. So the goal for today is to make this more formal, at least a little bit more formal than what we said just now. Okay, so in order to explain this, and this is the way I like to see it, is to study a graph associated to a surface. So in particular, an oriented graph. So oriented graph means a graph for which all the edges have a direction. So it's a set of vertices, a set of edges between two vertices, in such a way that the edge has a direction, it goes from one to the other. So this is very, very simple. You shouldn't think of it too much as from a topological point of view. It's really a very simple object just to represent surfaces, just to represent our forest of surfaces. The only thing to keep in mind is that this graph is huge. It's really very, very big. And we have many, many connected components where, as we can see in a few minutes. Okay, so you can imagine what the vertices are going to be. The vertices is going to be smooth algebraic surfaces. So each vertex is a smooth projective variety of dimension 2. And again, we're working with a complex number. Although what I'm saying now really makes no difference on which field you work on. And what are the arrows? So we were talking about edges. So I call them arrows just because they have an orientation, they have a direction. So if we take a surface y and a surface x, or in other words, a vertex y and a vertex x, then an arrow from y to x corresponds to saying that y is the blow up of x at a given point. So the surface x, for simplicity, is taken to be smooth. So any point can be taken as a blow up. And this will give us a new surface y, which is smooth. So if these things happen, then we say that there exists an arrow from y to x, or vice versa. So you see, we define the graph. It's of course, as I said before, it's a very big graph, but it's well defined. So let me study a little bit this graph. Let me say a few properties. So this graph will have many, even if we just consider a set of algebraic surfaces, so dimension 2, we have many, many connected components. So how should we think connected components? Again, without thinking too much about topology, it just means that a connected component is a set of vertices which can be reached by a union of arrows without thinking at the moment, without thinking about the direction. Okay, so if we cannot reach one vertex from the other through some arrows, it means that these two vertices belongs to two different connected components. Okay, so let's focus for a moment on a single connected component. So let's take the black one, for instance, the one on the left. So you see that there are infinitely many vertices, as we said before, because starting from any one, like for instance this one here, I can blow up as many points as I want, and I can go up as much as I want. But of course, starting from one, I can also go down, right? Because maybe my vertex is defined by a surface which emits a blow down, the opposite of a blow up, from here to, from this vertex to another vertex. So the reason why there's a question mark here is because we know very much that we can go up as much as we want. Why up? I mean, going backwards. If you think of arrows to be a direction, going up means to go opposite to the direction of the arrows. And so we can go up as much as we want, but the question is, how about down? How often can we go down? So this is the question of Birational geometry. Can we find a vertex from which there are no more arrows starting from it? So in other words, this would be like a target. It would be the final goal of, if we constrain ourselves inside the connected components, it would be our final object. And we'll see, I mean, of course, there are many questions we can ask. First of all, is there such an object? Secondly, how many such objects there are inside the connected components? So even in the case of curves, of course, connected components for curves is just one vertex. There is no blow up for curves. So each connected component corresponds to one curve, one point, one curve, one single curve. So but even in the case of curves, the number of connected components is infinitely many. Not only infinitely many, it's we saw before, even if we pick the genus of the curve, it would be represented by a variety which has dimension 3g minus 3. So it's really huge. But let's not worry about this. Okay, so this can be considered as a definition. Two surfaces which are connecting the same, which are containing the same connected components are said to be birational. Of course, this is not the standard definition. It's just by looking at this game here. We'll see a more, how to say, standard definition in a few minutes. But so we defined the equivalence class we were talking about just now. Okay, so two vertices are equivalent to each other, or in other words, two surfaces are birational, if they contain the same connected component in this graph. Okay, so now let's see some properties of this description of these graphs. Okay, first of all, let's give a more standard definition of being birational. So we say that two algebraic surfaces are birational if and only if there exist proper subvarieties x1 inside x and y1 inside y, in such a way that if we remove x1 from x and y1 from y, then x minus x1 is isomorphic to y minus y1. Okay, so this is a more standard definition, and of course it can be proven that it's exactly coincide with the definition we gave in the previous slide. But this definition will be useful in the future when we want to consider birational geometry in higher dimension. Okay, so now let's see some more simple properties of this huge graph. So first of all, it's possible to show that, and I'm going to present a very, very simple proof in 1 minute, that there are no oriented cycles inside this graph. So oriented cycle, it's easier to see a picture rather than define it. It just means a cycle where I start from a point and after a while I end up on the same point. But what I mean is that this path follows a direction. It's possible that, I'm not saying that the graph is simply connected, because it's possible that we have two vertices which are connected by two different paths going the same way. But what I'm saying is that it's not possible to find a non-trivial path which finds itself after a while on the same vertex. So the proof is very simple, because every time we have an arrow from one cursor to the other, so in other words, every time we have a blow up of a surface to another surface, so the Betti number of the surface above, the first Betti number of the surface above is greater than the Betti number, the corresponding Betti number of the surface below. It's strictly greater. And this is clearly a positive, a non-negative integer. So clearly, if we repeat this step finitely many times, we cannot happen to be in the same vertex again, because otherwise the Betti number must have increased again. And this is not possible in our operations. Okay, and using exactly the same proof, it's possible to show that the graph does not admit an infinite chain. So again, here we need to be careful what we mean by infinite chain. What I mean is exactly what is described in this picture. If you start from any given vertex and I start walking, I cannot walk forever, because there are no such infinite chains. So at some point, we need to stop. Okay, and again, the proof is what we said before. If you fix a vertex, the Betti number, it's a non-negative positive integer, and this number cannot decrease forever. Actually, we can even give a very explicit bound on the number of paths and the number of arrows starting from a surface X. But of course, it's possible, and actually it's always the case, that given a vertex, we find infinitely many arrows above our vertex. Okay, so let's put these two simple things together. The fact that there are no oriented cycles and there are no infinite chains starting from a vertex. Then if you think about this, this implies that if we start from any surface, any algebraic surface, at some point, after finitely many steps, we need to reach a target. We need to reach a point which does not emit any more arrows starting from it. So this looks very simple, and it is not hard, but somehow it can be seen as it's an object of study of many, many works of several mathematicians. In particular, here I mentioned Castelnuovo, Enrique, and Severi, but there are many more involved, which is somehow the beginning of the Birational geometry of projective varieties. So in this case, we only consider a case of surfaces, complex surfaces. But the idea is that if in this big graph, for each connected components, we can always find a target. So an object from which there are no more arrows starting from it. So if you remember the picture before, where we have many different objects in our connected components, and we can go up as much as we want. Oops, sorry. But no matter how high we go, we will never be able to go, if we start from any surface X, like in this case represented by this object here, by this vertex here, there is always a path that at some point will end, because you see, there are no oriented cycles, so it will never go back to X, or will never repeat itself at any vertex, and there are no infinite chains. So at some point we have to arrive to target. And this target is usually called the minimal model of our surface. So of course, this is not the end of the story. You can ask yourself, how many such minimal models there are? How many targets there are? And if there is more than one, how are they related between each other? Okay, but for the time being, let's stop. I mean, let's focus on the original question. How can we extend this picture in higher dimension? Is there something similar in higher dimension? And it is possible. I mean, at least we have an idea how to do it, but there are still many, and we'll see what the problems are. There are still many, many open problems in this study. But let's start from the very beginning. Let's consider what we did before in higher dimension. So at this point, the dimension of our variety is arbitrary. So in particular, since we already saw dimension 2, let's assume the dimension is at least 3. So now we give as a definition what we say before as a property. X and Y are two varieties, and they're said to be birational if we can find the subvariety x1 inside X, which is proper, and subvariety y1 inside Y, in such a way that if I remove x1 from X and y1 from Y, then they're isomorphic. So remember, in the case of the blow up, x1 correspond, if Y is a blow up of X, then x1 correspond to a point, and y1 just now corresponded to a line. In higher dimension, many more things can happen. I mean, it's not only, of course, you move a point at the sphere. It can be much more complicated than this, but the idea is very similar. We remove proper subvarieties and we attach new one. So let's see some properties like we did before. So one question that you can ask yourself is, assume that two varieties are birational. This is an equivalent class. Which property is birational invariant? So by this we mean, suppose that X satisfies some properties. Are these properties also true for Y if Y is birational to X? And this is true for many, many properties, many interesting properties that in birational geometry we study. So first of all, the first one is the easiest one. The dimension is a birational invariant. So what does it mean? It means that if X and Y are birational, then they both have the same dimension. So for the time being, let's suppose that X and Y are smooth, although we should consider also singular varieties. And the reason why we need to consider also singular varieties is because this picture, it's much better understood, it's much better behaved if we don't throw away singular varieties. The graph becomes, we're going to construct a graph, and the graph becomes much nicer if we don't focus only on smooth varieties. So this is slightly different in the case than the case of surfaces, where it's okay to consider only smooth varieties. So there are singularities. You might have heard the word terminal and so on, which are best behaved in respect of this program. But I'm not going to go into this. I'm going to hide the details, and I'm just pretending that there is no such an issue. There is not such a technical issue. Okay, so the most important, although this is the case, the most important property from this point of view is a very important theorem due to Runaka, which says that every variety, it's always birational to a smooth variety. So even if we focus only sorry, even if we focus on all the varieties, no matter how singular they are, we can always find inside the equivalence class at least one, but of course many, infinitely many, varieties which are smooth and which are birational to the region 1. Okay, so this is a deep theorem. It's very hard to prove. But we take it as granted. Nowadays, this theorem has been used so often that we don't even cite it anymore because it belongs to the classic gadgets of a birational geometry. Okay, so what is the goal for us? The goal for us, so for a birational geometer, is to define a new oriented graph which is similar to the one that we consider in the case of surfaces. So the connected components should coincide with the classes of birational varieties. So this can be achieved somehow, but it's not easy. I mean, it will take some work. So let's see some of the ingredients. So first of all, vertices are easy to describe. I'm going to take every algebraic varieties. If you want, we can fix the dimension. But since being the dimension is birational invariant, it doesn't really matter. I mean, different connected components we have will be represented by varieties for which every variety inside these connected components have the same dimension. So it doesn't really matter if we fix the dimension. Now, what about errors? So here we can not only consider blow-ups. So I'm going to be very naive here. I'm going to say that there is an error. This is very vague. It can be made formal. But for the sake of this lecture, let me just give a vague idea. So first of all, y and x need to be birational, of course. And somehow y must contain more curves than x of positive curvature. So again, the positive curvature here means it's not very precise, of course. If you want something more precise, it means that it's a curve C inside Y, which has negative canonical degree. So in other words, ky times C is less than 0, where ky is the canonical divisor, and it can be thought as the divisor associated to the minus the first joint class of Y. Again, I'm not going to use this language in the future, so it doesn't really matter if we understand this or not at this point. Of course, it will be useful to understand birational geometry, but for the sake of this lecture, I'm not going to need it. Okay, so this is very naive, but it can be made formal. It can be made in such a way that we have an idea of how to define errors. So the question is, I mean, since this is very vague, does this graph even exist? This is one of the questions that we can ask. And if the graph exists, does it have the same properties that the graph of surfaces had? So the answer is yes in many cases, actually in all the cases by now, at least what I'm going to say. So first of all, let's focus in dimension 3. This is the work which started by Mori. Mori in the 80s, so many years after, it took a lot of years after the work of the Italian school of the beginning of the last century to come out with this picture in higher dimension. So in the case of dimension 3, lots is known. And again, here I mentioned some names. There are many, many more. But let me just say that this program, the Minimal Model Program, which is the study of varieties up to birational equivalence, it's also called the Mori's program because it really was started by Mori. So first of all, it's possible to show that what it did is to show that this graph always exists in dimension 3. So what does it mean? Well, if you want a technical language, what really means is that flip exists. And there's much more. There's also the Kohn theorem and the base point free theorem. But the main difficult step is to show the existence of flips. I'm not going to explain what these are. There are surgeries among varieties, which allows to talk about steps from one to the other. Okay, the second thing that is possible to show, and what is shown, And this is not very hard once we know what the properties of the graph is that this graph does not emit oriented cycles in any dimension, so in particular in dimension 3. Of course, first we need to show the existence before we can show the properties. But okay, assuming that the graph exists, then it's possible to show, and this is not hard, that there are no infinitely cycles inside this graph. So there are no oriented cycles, sorry, inside this graph. So the idea is different from the case of surfaces. From the case of surfaces, we use a proof which is topological, strictly topological. In the case of higher dimensional geometry, the proof depends on the study of singularities of the varieties. Again, it's not easy, it's not obvious, but it's well understood by now. Also, except in the case of surfaces, in dimension 3, and this is very important that we emphasize the fact that it's only known in dimension 3, there are no, we know that there are no infinitely chains starting from a given vertex. So, in other words, if we start from a given vertex, we can never go back to our original starting point, and we can never walk forever. So at some point, we need to reach a target. So I emphasize here that n must be equal to 3. The dimension of the variety must be equal to 3. And the reason why I emphasize this is because even up to now, as written like in this way, in this generality, is not known if this is true in higher dimension. Although we do expect to be true, but we don't have a proof of this fact in higher dimension yet. There are a lot of works, and we're going to talk about some of them. But I just want to emphasize this is a very difficult problem, even up to now. Okay, but in dimension 3, if we put all this together, and if we focus inside a connected component of a given variety x, so in other words, of a given vertex x, then we know that since there are no oriented cycles and since there are no infinite chains, we can always start from a variety x, run through this path here, the red path here, and eventually we'll arrive to a model or to a vertex which does not emit any more errors. So, as I said, we're not claiming that it's unique. It's actually not, it's not unique in general, and we're not. There are many properties that I'm hiding here, but at least there is a special object here which represents our connected components, and this is called minimal model. In our language, it's called target, but in a more classic, in the common language of Birational geometry, it's called minimal model. At least in some cases, called minimal model. In other cases, some people might use different words, but for this lecture, let's just call it minimal model. Okay, so the goal for now is to understand varieties, many properties of varieties for which we know how to extend this picture in higher dimension. So let me focus on the set of varieties of general type first. So variety X is said to be of general type. So this is very naive. It's not the correct definition, but very vaguely, we know that a variety is defined inside the projective space Pn. So let's fix the dimension, n. So if the polynomials that define the variety have sufficiently high degree, whatever it means, then we say that the variety is of general type. So if you want a precise definition, what this means is that if we take the canonical divisor of x, and we look at all the tensor power, or in other words, all the multiples of the canonical divisors, and we look at the global section of this divisor, of the line bundle associated with this divisor, I'm assuming that the x is smooth for the time being, then the dimension of this vector space is like a polynomial of dimension equal to the dimension of x. So in other words, it can be written, it can be thought of C times m to the dimension of x. I'm not sure what this point is, where C is a positive constant. Okay, again, I'm not going to use this language much in the future. I'm just giving, just wanted to give a precise definition of what general type means. Okay, so let me give an example, which is somehow related to my vague definition. So if we fix a variety x, which is defined by unique polynomial, so it's a hypersurface, and assume that it's smooth. So in other words, there are no critical points for the polynomial defining x, at least inside the projective space, of course. Then it's what it means to be of general type is that the degree of f is greater than n plus 1. So it's a very simple definition. I mean, from this point of view, it's a very, very simple definition. And you see that if you agree with this definition, then most of the hypersurfaces will be of general type. At least most of the smooth hypersurface will be of general type. Because if f is a random polynomial, then for sure we'll have degree greater than n plus 1. So a nice property of this fact of being of general type is that, although I didn't, I'm not able to prove it or anything like that, but being of general type is a birational property. So in other words, if you have two varieties which are birational to each other, and one is general type, then also the other one is. So we want to understand the picture for this particular case, for varieties of general type. But although I use the word particular, really most of the varieties are of general type. I mean, if you think about the curves of curves, being of general type means being hyperbolic. So we saw before that most of the curves are hyperbolic. So if you want to bet, if you take a random variety, you want to bet if it's general type or not, you surely can bet all your money, because if it's really random, then for sure it's going to be a general type. Okay, so something we proved several years ago is that so it doesn't matter if you consider varieties of general type or not. So after the work of Mori and many others, a few years ago, we were able to show that flips always exist. So this kind of surgeries we were talking about before always exist. So in other words, there is a way to make this graph precise in every dimension, to give a formal definition in any dimension. Okay, so why did I define varieties of general type? Well, the reason why I define varieties of general type is because in this case, in this particular case, if we consider the connected components of varieties of general type, and remember, since being general type is birational property, it doesn't really matter if you take one or if you take all of them. Inside the connected components, they are either all of general type or none of them is. The target always exists. Okay, so be careful, because I'm not claiming that any path will terminate at some point. We're not claiming that there are no infinite paths. So in other words, it's possible that there are infinite, I mean, we don't know. We don't think that there exists, but a priori, there could be some infinite paths. So in other words, if you are inside the connected components, you're not allowed to walk blindfolded. You need to open your eyes. If you choose the correct path, given starting from a vertex X, then you always end up on a target. A target is a minimal model. So in other words, a variety that does not emit any starting point, any arrow starting from it. Okay, it's possible that there are some infinite chains somewhere else, but let's not worry about that. For sure, we'll be able to find the target. It could be that there is more than one target, but actually, it's possible to show that there are most finitely many minimal models inside the connected components of a variety of general type. And many more properties are known. But for the time being, let's focus on the fact that we can always find a minimal model, something that represents our variety in a nice way. So from a more precise point of view, a minimal model satisfies the property that it's the canonical divisor of such a variety is non-negative for every curve containing such a variety. So this is the formal way to define a minimal model. It's possible to show that it's equivalent to being a target, because remember, error in our graph means that we are getting rid of curves which have negative degree with respect to the canonical divisor. So if there are no such curve, then there is no error starting from our variety. Okay, so now we consider varieties of general type. So now let's consider some varieties which are different, completely different connected components. And these are called Uniruled varieties. So Uniruled varieties, it's a variety such that for any point of the variety, we can find a morphism from P1 to X. If you want, we can think of it as an holomorphic map if we work with the complex numbers, or as an algebraic map. It really makes no difference because P1 and X are compact. Such that, of course, I didn't write it, but it's non-trivial. So in other words, it's non-constant. Otherwise, it wouldn't be an interesting definition. But more importantly, the point X that we consider is contained inside the image of P1. So we should take X to be smooth in order for this to be, well, I mean, in order to this make sense. But besides this technical aspect, the idea is clear. For any point, there exists a curve which looks like P1, looks like a sphere. So an example, very simple example is Pn. Why? Because for any point of Pn, there exists a line, and the line's a sphere. I mean, a P1, which is a line, coincides with a sphere. So it means that Pn is uniruled. But there are many more interesting varieties which are uniruled. On the other hand, like I said before, varieties of general types are never uniruled. So we're really considering a completely different class of varieties. And as we say before, we want this property to be birational for us to be interesting, for us birational geometers to be interesting. So indeed, this is the case. So if we take two varieties, at least smooth, given the definition that I gave, which are birational, then one is uniruled if and only if the other one is. So if we consider connected component of X, it doesn't really matter which representative you choose. If one is uniruled, all of them will be uniruled. Okay, so what do we know about uniruled varieties? So again, as I said before, we always know the graph exists. This was possible to show in any generality. But in the case of uniruled varieties, we also know the existence of a target. It's strange because in these two opposite cases, we know the existence of target. What we need to study is, what we still need to study is whatever is in the middle. Okay, so what is the target here? So this means again that there is a path which terminates to a special object from which there are no more errors. But in this case, it's not, I mean, different people use different language, but it's not strictly speaking a minimal model. So in other words, it does not admit the property that I mentioned before about the canonical divisor being non-negative on every curve. So what we say instead is that y, I mean, what is possible to show is that y emits a modifiable space. So what does it mean? Maybe the picture will clarify what really this means. So it means that there is a morphism from y to z, where z has always dimension less than y. So y has the same dimension of x because y and x are birational, but z is always smaller. So we're making our object smaller, and this is good because z being of a smaller dimension will be easier to study compared to y or compared to x. But what else can we say? Well, the fiber of this morphism, in other words, the preimage of this of a point through this morphism, for almost all z, I'm not going to be very precise here, the fiber emits a metric with positive curvature. So more correctly, this means that the canonical divisor of F, where F is the fiber, it's anti-ample. So minus KF is ample. So in other words, F is a Fano variety. Okay, so what does it mean almost all that? It means again that if you're not unlucky, if you choose a random point, if you're not unlucky, then this property will be true. You can say that is measured zero, but it's, I mean, the place where this is not true is measured zero, but it's much, much stronger than this. It's really a subvariety of Z for which things, a proper subvariety of Z for which things go wrong. Okay, so let me ask a question which is still very open, and I think it's very interesting from many points of view. There is a lot of work around this idea lately, and I should say that there is not much evidence for this to be true, but it will be very interesting to know, at least from my point of view, to know if this conjecture, if this question has a positive answer. So can we do better than this? So it's possible to show that there are many varieties which are called Fano, so many varieties for which they emit positive curvature, but do not emit a metric with constant positive curvature. These are called Keller-Einstein metric. So it's possible that we found a modifiable space for which the fiber has a metric with positive curvature, but not a Keller-Einstein metric. So can we find another more, if this is the case, can we find another modifiable space, so another Y, another variety Y, which is Birational to X or Birational to Y, the original Y, which also emits a fibration, but this new fibration has the property that the fiber emits a Keller-Einstein metric. So this is very much related to the study of K-stable varieties, which has been intensively studied over the last 10 years. And many very interesting open questions have been solved over the last few years, both using analysis and using algebraic geometry. It's really a point where differential geometers meet algebraic geometers. So it's really a very interesting study. Okay, so as I said before, we expect to always be able to find a target. So the conjecture is more precise. Suppose that X is a smooth variety, which is not uniruled. So it's not one that we are considering just now, which is Birational to something which emits a modifiable space. Can we always find a target inside the connected components of X? So in other words, a variety X mean, which does not emit any more errors starting from it, and in particular emits a metric with curvature less than 0. So if the target exists, then the answer is yes. So in other words, we can find such a metric, at least if we don't worry too much about singularity. So if the target is moved, at least this is true. Okay, so I'm not going to be very precise what metric means here. Let me just say from algebraic geometry point of view, means what we always say is that the canonical divisor is non-negative on every curve contained in the variety. So this is true if we can show that there are no infinite chains in the connected components of X. But again, in dimension bigger than 3, this is a very open problem. We don't know the answer, even in the case of variety of general type. And as I mentioned, it's true in dimension 3. And it's true for varieties of general type, although it's not because we know that, as I said a few times, it's not because we know that there are no infinite chains, but for different reasons. But also, what we expect is that this final object, this target, emits some very interesting properties. And this is the goal of abundance conjecture. And this, again, a very open conjecture, except in dimension 3, where we know to be, and lower, of course, where we know to be true. So the picture is similar to in the case of modifiable space, but let me clarify. So we expect that the minimal model, So a variety satisfies this property here, or in other words, a variety which does not emit any more arrows starting from it, which is not uniruled, emits a morphism into Z with connected fibers, and such that either this is a bit vague, but either Z it's Birational, so in other words, phi is a Birational morphism, and Z emits a metric with negative curvature. So in other words, we can think of Z to be hyperbolic, and actually we can even make it constant negative curvature. So in other words, we're saying the case Z is ample. Or, like in the case of Mori-fiber space, the dimension of Z is strictly less than the dimension of X, or the mirror models. And for almost all Z, whatever this means, the fibers emit a metric with zero curvature. So it's a Calabi R. In other words, the canonical divisor of F, it's somehow equal to zero. So in particular, it's zero on every curve of F. And we know that this object emits a metric with zero curvature, so of course it's a Klein-Einstein. Okay, so this saying, I mean these conjectures, this says that after playing some games, we can always reduce to a final object, mirror model, which can be decomposed into three varieties. Either like before in the previous slide, which are final varieties, possibly with a Klein-Einstein metric. We don't know that yet. So by other words, with a positive, at least we know that it's going to be with a positive curvature metric. Or it can be decomposed in other objects, which have either negative curvature or zero curvature. So really, these are three building blocks on which varieties can be constructed. So this somehow justifies why all this is important. Okay, so now, sorry, here there's another typo. I used some slides in Italian, so sorry about that. So now let me focus on some new study of the Minimal Model program in the theory of foliations. And the reason why I talk about theory of foliation, because it's very much related with what we were saying before, both in terms of the goal and in terms of the methods. So what do I mean by this? Foliation, we expect foliation to be the main tool to solve some of the outstanding conjecture I mentioned just now, in particular the abundance conjecture. We think that many people really think that foliation would, and I will justify why. I mean, actually, this has already been the case so far. Foliation will play a big role in the proof of abundance conjecture, if this conjecture will ever be proven. So let me start from the definition of a foliation. A foliation on a given variety X somehow corresponds to the composition of X in a disjoint union of analytic subvariety X. So these are not algebraic varieties. It's really, we should think of them to be analytic subvarieties. Sometimes the situation is even worse than this. But let's consider this example where I will look at it in more details in a few minutes. But basically, we should think of this to be many, many varieties whose union is equal to X. So each of this variety can be thought as the solution of some differential equation. So for instance, let's consider this particular picture that we had before. So let's fix a constant C. C is a number. It's a complex number since we're working with the complex numbers. And let's consider the function xy minus c. So each of these curves correspond to the curve given by, so this is algebraic. Of course, we can do many different curves which are not algebraic, but correspond to xc, correspond to a set of solution of f equal to 0. By f, it's a solution of the differential equation written here. It's a partial differential equation. This can be, of course, very easy to check. Okay, no matter what C is, it will always satisfy, F will always satisfy this property. Okay, so this is more or less what a foliation is. It's possible to give a more precise definition, but as a subsheaf of the tangent bundle of X, or the tangent sheaf if the X is similar, but I'll prefer not to give too many technical details. So let's see instead an example, a very simple example. So if we assume that X to Z is a fibration, so in other words, a morphism with connected fibers, then each fiber is an analytic subvariety, possibly singular, but it's an analytic subvariety of X. And the union of these subvarieties is the whole variety X. So these are the leaves of the foliation that we're considering. Okay, so each fibration coincides with a foliation. Sorry, not coincide, induces a foliation. So this is why it's related with what we were talking about before. The abundance conjecture, it's about constructing a fibration. So can we start by considering the foliation? And this is not something new. This has been around for a long time. So these are very special example of fibrations, of foliation, sorry. And they're called algebraic integral foliations. So why are they special? Well, first of all, every single leaf here, it's algebraic. As I mentioned before, there are many foliation on algebraic varieties which are not, whose leaves are not algebraic. So, but still they're worth considering. Okay, so one property about foliation is not striking, it's nothing special, but nevertheless it's useful, is that if you have two birational varieties, I mean two varieties which are birational and one emits a foliation, then also the other one will emit a natural induced foliation hit. So if F is the foliation on X, denoted by Fy, the foliation on Y. This is, and note that this is not true for fibration. I mean, at least it's not true that if one variety emits a fibration, and the other one is birational to the given one, then the second one would be also emitting a fibration. So if you want a very simple example, P1 times P1 and P2 are birational within each other. The reason is because they both contain a copy of C2. If you remove suitable subvarieties from both of them. But the first one emits two interesting fibrations, which are the projections. On the other hand, it's possible to show that P2 only emits trivial fibrations, namely the identity or the map to a point. So, of course, this is not a big deal, but this is somehow one advantage of working foliation. More importantly, if we know that abundance holds true, then this implies that every variety which is not Uniruled emits a natural foliation, which is algebraic integrable. Okay, so what is this? Well, we know that every variety is birational to a minimal model if everything that we said before is true. So many open questions still need to be solved, but assuming that the conjecture is true, then we'll obtain this. And the goal, the target variety emits a fibration. So in particular, emits a foliation. And since the foliation can be induced on the region K, then the first foliation will also, the first variety also emits an algebraic integrable foliation. So as I mentioned before, this is not new. In dimension 3, here, sorry, this is another typo, abundance follows from foliation theory. This was proven by Miyaka in the 80s. Of course, there are many more ingredients involved, but foliation theory plays a very big role in the proof of abundance. So again, it's not completely unexpected to believe that foliation will play a role even in higher dimension. So one question is that we can ask, which is somehow similar to try to prove these kind of statements, but in terms of foliations. Given a foliation on a variety X, can we find a new variety Y, which is birational to X, and for which the induced foliation emits leaf which all have same curvature, I mean curvature of the same sign. So they are either positive or negative or zero curvature. This is very vague, but somehow this justifies the Minimal Model program for foliations. So in order to achieve this, we really want to construct a new oriented graph. So trying to generalize what we were doing before, to make it even wider somehow, because given a variety X, there are many, many foliations. So what are the vertices? The vertices are pairs where X is algebraic variety and F is a foliation X. So as I mentioned, this is a larger graph than before because every given algebraic variety emits many, many foliation. Now, what are the errors of this graph? So first of all, we fix two pairs, YG and XF, where G is a foliation Y and F is a foliation X. Y and X, we assume them to be birational, and F is the foliation induced by G, or vice versa. And the idea, although this is very vague, is that Y should contain more curves, which are positive curvature, and also are contained inside leaves of G, compared to X. So in other words, we're getting rid of curves which have negative canonical degree with respect to G. So it's possible to define, and this is very simple if we give a proper definition of foliation, a canonical divisor for a foliation. And so in particular, it's possible to define intersection theory between the canonical divisor of the foliation G with any curve C on the variety Y. So we want to get rid of these curves, exactly like before. So for instance, there are many of the properties we said before can be defined for foliations. So for instance, foliation is called Uniruled. If for any point we can find a morphism, which is non-trivial, of course, from V1 to X, and which contains the point we're considering. But more importantly, FP1, the image of P1 is contained in a leaf of F. So in other words, it's tangent to the foliation. So I should say that we can repeat the same game as we did before. We can study paths, and many of the results are very similar to before. We can study cycles and so on. And thanks to the work of Brunella McQuillan, and actually I should add a few other people like Mendes, it's possible to show that for surfaces, this picture works very well, exactly like in the case of the Minimal Model Program for surfaces, which is due to the Italian school of the previous century. So in other words, we can always, starting from any pair XF, we can always find a path which ends up into a target, which can be called a Minimal model. So if the foliation is not uniruled, then the path will have the property that the foliation which you obtain is minimal, in the sense that, again, it's positive with respect to any curve which is contained in the variety underlying the foliation. So this is the ultimate goal for the Minimal Model program for foliations. So of course we can ask ourselves, can we extend this picture in higher dimension? Well, here, of course, there are many more open problems, since this is a much more recent program than in the case of varieties. But at least in dimension 3, many things happen to be true. I mean, many results that are true for varieties happen to be true for foliations. So first of all, let's define the rank of the foliation as the dimension of a generic leaf of the foliation. So we should think of the classic MMP to coincide with MMP for foliation when rank it's equal to the dimension of X, because in this case, the foliation is trivial. So, but all the properties we said coincide with the property we're considering now. So in other words, really the MMP, the classic MMP, it's a subset of the MMP for foliations in a sense, where the rank is considered to be maximum in this particular case. So clearly in dimension 3, the MMP is known to hold true for rank equal to 3, because we know that MMP holds for classical projective variety in dimension 3. So what we proved a few years ago is that this MMP holds for foliation rank 3 in dimension 3. So in other words, there is a graph. Not only there is a graph, we can always find a target because there is no infinite path and there are no oriented cycles. And then, so independently, this has been done from different point of view by McQuillan, using morpholation theory, and by us, sorry, I should have said it, in collaboration with Calvin Spicer, using more methods from classical Birational geometries. We know that the same is true for foliations of rank 1. I should say McQuillan does it in every dimension, but in a less broad point of view. We only focus on dimension 3, but in a more general setting, but for foliation rank 1. So combining these results together, it means that in dimension 3, the classical MMP can be extended in full generality for foliations. Okay, I will stop here. Thanks very much for your attention, and I'm looking forward for questions or for comments or for any chats about this. Thank you.